Okay. Hi, Anne. So good to see you
Hi.
again.
Yes, and you, and you.
And thank you again for agreeing to have an interview on a very specific mathematical idea and how it is treated in math curricula across different contexts.
Yes, and it's a big issue. Multiplicative reasoning, multiplicative structure. So much of what we do in mathematics depends on having a multiplicative understanding of the relationship between quantities, rates of change, proportionality ratio, enlargement, scaling, all those things are about multiplicative relationships between quantities. And too often, what happens in primary school, because of the focus on multiplication tables, is given as repeated addition, or in extreme versions, just learnt facts, which don't really have any meaning behind them. And that can be a very damaging start to having the word multiplication in your head, because it limits the word multiplication to these learned facts with whole numbers. And in fact, the roots of a more complex understanding of multiplication are already in children's knowledge and awareness from their ordinary everyday activities of pouring stuff, dealing with stuff that you can't count, really. Any stuff that you can't count can still have multiplicative relationships with each other. So if you have a couple of containers with water in, and you can find out how much of one container can go into the other, or how many of the smaller container can go into the big container. Okay, you're counting those, you're certainly counting those, but you may not be able to count them in whole numbers. And also, you may not have them all there. You may say to yourself, well, I'm kind of adding these. So you could get away with the repeated addition. If this holds half a cup and this holds 5 cups or something, you can pour in and you can repeatedly add halves, and you have to tally them somewhere. And that'll tell you how many you need. And that's division. And it's a tricky one, because you're dividing by a half. You're saying how many halves go into 10. So there's a very complicated, complex understanding of the multiplicative relationship that is lurking in there. And it gets even more complex if I've got a holder of 10 measures of some sort and a holder of a half measure. And I want to show that this 10 is 20 of these little ones. Well, I can get 20 of those little ones and line them up, and I can fill them all up. And then 20 of those fill this thing. But also, I can take one of those little ones and a big 10, and I can pour and say, well, that's one measure. And then I can pour and say another measure. I don't need to have 10 of the little ones to know that 10 of those go into that. So if I've got the little 10s, then I can call it repeated addition, that they go into here, and repeated subtraction, that they come out of there. But if I've only got one, then I've got to have the roots of the idea of scaling. That I've got to multiply this by 20 to pop it into there, to fill it in there. So now what I've just said, of course, if you will go back and analyze what I've just said, there's all kinds of language that doesn't sound like multiplicative language. It sounds like adding up. It sounds like taking away. It sounds like scaling. It sounds like division, perhaps. How many of these go into this? The language of multiplication as times isn't there, and certainly repeated addition isn't there. I can express it in use of the word times. I can say this, a half times 20 makes 10, or 20 times a half makes 10. It's yeah, it's all a bit where do we go with this? But
Yeah.
but where you go with it is when you're doing pouring things with children, instead of just thinking of science or cooking or whatever you're doing, you can begin to use the language of multiplication.
Yeah, perhaps I should remind listeners why we're talking about multiplication. In the previous interview with John, Mason, and you, we raised that point of why multiplication is taught as repeated addition, and why it is counterproductive to what we want young kids to know and understand with regards to the importance of multiplicative reasoning, and how it is essential in developing other very important mathematical concepts. So perhaps we should, and we will, I hope we will be able to provide some helpful basic elements to think about when we think about multiplicative structures, such as units, such as scaling, such as perhaps thinking about the difference between discrete objects versus continuous objects, which you mentioned. But let's start with what is the problem with teaching multiplicative reasoning as repeated addition. When and why does the rule expire at a later stage when we teach about fractions, for example?
Well, with fractions, suppose I've got to the place in the school curriculum where we suddenly have to multiply fractions. And by the way, that's in itself is a problem, the way that we do adding, subtracting, multiplying, dividing, and then we do all those things with fractions. Fractions are a natural outcome of thinking multiplicatively. I think I've just tried to show that this little measure is 1/20th of the big. If I had the big measure, if I could sort that out into 20 equal parts, then I would have the little measure. Well, when you're sorting something into 20 equal parts, you're making 20ths. So fractions naturally follow from understanding multiplication and division in a more holistic, liquid sense than merely the so many times so many whole numbers. And then, of course, if you're stuck in whole numbers, then when you start to do division, you run up against a big issue, because division can't just be done with whole numbers. And the word divide is quite useful for partitioning. I'm going to divide something up into so many equal parts. And so fractions become a natural kind of outcome of all this pouring idea. Anything you can do with pouring, you can also do, of course, with length. And so the models you have of numbers are really quite important. If the only models you've got of whole numbers are discrete blobs, then you can't really deal with fractions in a meaningful sense. Chopping up pizzas doesn't do it, because it gives you very, very limited images of fractions. But if you have number line images or rods to represent quantities, then the fractions kind of come relatively easily from the way that you talk about relationships between quantities. Now I'm going to try to share a screen with you. Are we managing it? Can you see?
Yes, I can see the slides. Yeah.
Okay. So I've chosen the colors that are in Cuisenaire rods. So you've got an orangey browny bar, and you've got 5 equal red bars, which give you the same length. And when you've got bars that are the same length, you can write that as an equality. So I can say the length of the orange bar is the same as 5 of the lengths of the red bar. And then on that slide, you've got several ways that you can write that. If I take A to be the length of the orange bar, then C to be the length of the red bar, and B, oh, well, that's interesting because B is not a length. The things I'm dealing with are lengths, are concrete, but B is not a length. B is the number of the red lengths. Now, when you're using these bars to do adding or subtracting, everything is lengths and everything is expressible in lengths. But here we've got a situation where there's clearly an equality going on, but B is not a length, it's a something else. And in this particular case, it's a counting. And I can write it as A equals BC or BC equals A. But I can also write it as the length of the orange bar divided by the number of red bars gives me the length of the red bar. Or the length of the orange bar divided by the length of the red bar gives me the number of red bars. So you've got rods, lengths of rods, numbers of rods. The answer of however you want to put it, the answer is 5 or a fifth or 2 or 10 or 1, depending on the question. And some of these answers are numbers and some of these answers are lengths. And some of these answers are whole numbers and some of these answers are fractions. So here's a situation that you can talk about a lot. You can ask lots of questions about it. And the idea of fractions comes naturally from the kinds of questions that you might ask. So there's no need to kind of bash on with multiplication and division and fractions, unit fractions and so on, as kind of separate beasts that have to be learnt about separately and in a particular order. You can have quite complex conversations with learners about this relationship that gives you doorways into fractions, into ratio, and into scaling, and as well as into multiplication tables, if you really want to do that. But I could ask you, supposing the length of the orange bar is 5, what's the length of each red bar? Supposing the length of the orange bar is 15, what's the length of each red bar? And I'm not asking you to answer. Supposing the orange bar is 20, what's the length of each red bar? And you can imagine children fiddling about with these and trying to work out what they could possibly be. And if children use, this is where it connects beautifully with measures as well, measures in non-standard units. I mean, it so happens that the red bar, the orange bar in Cuisenaire rods is 10 centimeters long, and that's a real nuisance Of course, in the States, you don't use centimeters, so you're happy. They're not going to make that connection. You just say 10 units. And you can see all sorts of conversations that can happen. I can imagine a diagram like this on a huge sheet of paper, and children writing all the way around the things that they have found out and the symbolic representation of it, and maybe other representations with other colors and other lengths that somehow get at this whole lovely world of division, multiplication, ratio, fractions, and so on.
And that really speaks to the need, or perhaps the call or the invitation for teachers to allow students to initiate their questions and thinking around mathematical concepts, rather than to be on the receiving end of this is the multiplication table, this is what you need to learn by heart, let's practice and practice and practice, which really doesn't contribute to a deeper understanding of multiplicative structures. So I hear you talk about the importance of sequencing the mathematical concepts, not necessarily waiting for, using Piaget as a guiding principle. First, you master a addition, then subtraction. Only then do we do multiplication and division. So we I wonder how the introduction of such more complex mathematical ideas can be done in, with the younger kids, right? Because if fractions is being introduced in grade 4, for example, we can actually, from what you're saying, we can actually introduce the thinking about fractions within this idea of quantitative relationship with kindergarten kids.
Yeah, you can. And in fact, Davidoff and followers of Davidoff actually do that. They have those conversations, and they have those conversations. And
when I read Davidoff, I found myself thinking about, I had an aha moment with regards to thinking about what is happening in classrooms, where the introduction of multiplicative structures is more traditionally done through discrete objects, right? How many apples do you have in? So anything that you can count. But then Davidoff's work really helped me see that what you used the word liquid quantities, which I love. I think it's very, very helpful.
Well, I just got fed up with the word continuous because it doesn't convey that. Yeah.
Discrete and continuous are creating some sort of a binary understanding. It's not this but that, but it's really changing the way we think about objects and what we can do with them. And you mentioned measurement using non-standardized units, which is so important, but we forget that we need to intentionally work with non-standardized units so that kids can better understand multiplicative structures.
Absolutely. And are willing to, when you see that diagram that I showed you, are willing to make that length, that brown, yellow, orange length, whatever it is, whatever you say it is. They can, because they're not always measuring everything in inches or whatever. Yeah.
So may I ask you, why should there be a shift in how multiplicative structures are taught or learned now in the 21st century with new expectations of learning objectives?
Because most of the things that you need mathematics for involve multiplicative relationships, and they're not usually small whole numbers. they're not usually amenable to knowing what 7/8 are. They're usually, it's usually much more of a structural thing. So it's the relationship, and being able to look at the relationship in a variety of ways and know that certain sorts of language and certain sorts of problem lead you to that sort of relationship.
Would it be too, yeah?
Well, I was going to say, if I go back to this thing here, can you see it? Is that all right?
Yeah.
I made a great thing about how the 5 is not a length. The 5 is the number of these lengths that you've got, and how important it is to be aware of that language, because when people are talking about whole number multiplication, you very often see this sort of diagram. And it matters whether the answer to your question is a number of rows or the answer to the question is some cabbages. That matters. Because one of those is the scalar and one of them is the quantity of the objects. But the answer is not really cabbages, it's a number of cabbages. It's always a number. And I don't always hear that in the language that I hear in primary schools. And that it matters whether we're talking about rows or whether we're talking about cabbages. But this image is not terribly helpful for moving to fractions. I mean, there are people who try to do that. There are people who are very committed to the idea of arrays as a model of multiplication. And I can see the reason for that. The reason for that is because you can move from an array model to an area model of multiplication, where you're not talking about rows and cabbages, and you're not talking about lengths and the number of lengths. You're just talking about 2 numbers. And when you're doing that, the area model really helps. And arrays and regions as models of multiplication help you move into a world where you're multiplying 2 numbers. Now, if you're modeling a real situation, you've got to bear in mind what those 2 numbers are. And if they're 2 lengths, then you're talking about an area. But most of the time when you're multiplying 2 numbers, one of them is a quantity of something, and the other one is the number of those quantities, like 5 times the length of the red thing. But I can see why people are very keen on the array model, and it obviously has some uses, because you can't do area with the linear model. You can't get there. So I'm not offering an easy alternative route at all. I'm saying, look, there's complicated stuff. And areas and regions are good models for multiplication, models for conceptualization of non-whole number calculations and of the distributive law. And Euclid used them for the distributive law quite happily. But for multiplying fractions, for instance, the area model is really lovely, because you can have one kind of fraction going one way and another kind of fraction going the other. And then you can see on your grid what the area has to be and what it looks like. And that it's, you can see what the common denominator means, why you multiply the 2 denominators together to get everything into the same kind of space. You can actually see that with the area model.
And would you say that we can do this kind of thinking, we can introduce or enable this kind of thinking with young kids, and how? And perhaps I should think about something that I do with my not mine. I always make that mistake with teacher candidates at Brock University, where I ask them to or embody an activity that has to do with Zeno's paradox. I asked him to, and that is actually an activity that was inspired by a paper published in For the Learning of Mathematics by George Gadanidis, and with fourth graders, where they were asked to get to a door. The question was, can you get out the door? Physically, of course they can, but then he introduced the mathematical concept, the mathematical condition. Just follow the condition of you are allowed to cover only half of the remaining distance to the door. And that was beautiful to read. And it was absolutely amazing to see with teacher candidates who are trying to make it, experience it. And you can see that they have very important questions. What do you mean by half? Or how big can my step be? Or what do you mean I can never get out of the door, mathematically speaking? Gadanidis finished his paper with some sort of a joke. This is how I see, I interpret this brilliant paper. He said that the following day, a child was asked by a parent, can the child take out the garbage? And the child said, well, mathematically speaking, I can't. The following day, the child asks the parent to go out to go eat out or go to the movies, and the parent says, well, mathematically speaking, we can't. So that's the way.
Yes.
About
there's
action.
so much. Well, there's so much you can do with very large and very small numbers with very young children, because they have an imagination and you can appeal to their imagination. And certainly with a concrete thing like that, you can appeal to it. And so, when you ask, can you do this with very young children? I was thinking, well, why would you want to multiply fractions with very young children? But what you can do is you can certainly give them a linear kind of an understanding of it. And you can also give them, let me just go and get some kit. Hang on. It's not very far away. Yeah. I have here Buzz Lightyear, and I have here Buzz Lightyear.
Oh, wow.
At some stage, they're going to look like the same size.
Almost, yeah.
Roughly there, something like that. And then they're going to get further and further and further and further away. And what's that all about in terms of numbers? Well, that takes you to the scaling, because if I have them in the same place, you can see they're not the same size. And you can start to talk about, well, how much bigger and how much smaller. And there's no way that adding these up, repeated addition, is going to give you this guy. You're just not going to be able to do it. But moving to and fro can. And that's absolutely fascinating, isn't it?
I wonder whether we need digital technology to show this on screen. Perhaps the screen helps better perceive that. It's all about scaling rather than repeated addition.
Well, you can do it like this, and you can say, oh my goodness, what's happening? And the kids will talk about it, and they'll know what's happening because they live in the world. And they know that sometimes people are very small. Oh, look, this is my granddad walking down the road. He's very small because I can cover him with my thumb. They know all that. So you can draw, again, a linear model and have them along there, along a line, and then you can decide where your eye has to be. Where does your eye have to be so that they look like the same size? Now, all of that is about multiplicative structure. And if you've got this understanding that you're talking about A equals B times C all the time, then you can do it in various ways, and you can have the measures and the measurements, and you can talk about how can we express this using this model of something equals something times something. How can we express that? And now can we move it around so that we can see one of them as the fraction of the other, a fraction of the height of the other? And I'm obviously ignoring the fact that the ratio of their areas is the squares and the ratio of their volumes is the cubes. But if you're just thinking about height, you know, that is a lovely thing. And it's so much more fun than going out and looking at trees, which is what people tend to do.
So,
Yeah.
so you were mentioning a few other mathematical concepts that are strongly associated with and a deep understanding of the concept of multiplicative structures. And I wonder what might be those additional mathematical concepts and how they are related to multiplicative structures.
Well, anything that you can write as A equals B times C is a multiplicative structure. So one example I really like, and that I find people thinking that sometimes when I'm talking about this, that it's all a bit fanciful. But when I talk about trigonometry to secondary teachers, they sometimes think, oh, yes, because the sine of an angle is the opposite side of a right-angled triangle divided by the length of the hypotenuse. And you can see that as a scaling like this. And you're writing this thing, sine of something equals something divided by something. Well, that's just an alternative way of writing the A equals B times C relationship. So can I write it like that? Well, yes, I can, because I can write the opposite side is the hypotenuse times the sine of the angle. And that tells me the whole story of a nest of similar right-angled triangles. Because this angle is staying the same, and this height is changing. And how is it changing? It's changing according to the length of the hypotenuse. And that relationship makes a lot of sense, thought about in those terms. And all that shuffling around that you have to do, make the sign of the thing the subject of the formula, you know, all that. you just have it in your hands already, because you know that anything that can be written as one thing equals two things multiplied together can be written in all those different forms. You know that. And so the rearranging of trig formulae, of the basic trig ratio formulae, isn't a great big sweaty thing. It's just you've met this new situation in which you can use something that you're familiar with.
May I suggest that when you say you're actually talking about the student, not the teacher, not the learner, not necessarily the teacher, so that the one experiencing it with these ideas is actively the student rather than the teacher, demonstrating this is how things work, this is how the procedure goes. And so it reminds me of again, the need perhaps with working with teacher candidates or even in-service teachers, how they can shift the teaching of multiplicative structures to something that is more openly and explicitly related to other mathematical concepts. And I'm thinking of a particular study that you and John did with participants, asking them to represent a third fraction, a third. Could you talk about that a bit?
Gosh, I can't remember that really. But if you did ask people to represent a third, I think you'd probably get some chopped up pizzas.
Mhm.
If you're lucky, you might get a rectangle that is sliced like that, which is quite useful because then you can go on from that diagram to, okay, what's 2/5 of a third?
Mhm.
And then you can say, oh, well, if I chop it into fifths this way, having chopped it into thirds that way, then I can see where 2/5 of a third is and what it looks like. So that's if you're lucky. Or you might get drawings of dots or something. A third. You might get a number on a number line. And
Really? That was your conclusion in that paper, which
this
which I found very interesting.
this is interesting because I look in textbooks sometimes at what's their linear model of fractions and how is it labeled, because it matters. If the journey that they're if what they've drawn is a journey from 0 along a number line, then a third is a third of the way to unity. But if they haven't made that into a journey, if they've just said this is 1, then any of those thirds could be called the third, a third. So it really matters. And I see lots of textbooks where there's a strip with of squares, and you're asked to colour in a third, and there are 9 of them, and you can colour in any 3. Any 3 is considered correct. But if it's got a 0 at one end and a 1 at the other, then you can't do that. 1/3 is the journey, and the third is the position. And there's confusion there. And it's confusion between a journey or a vector or a number line and a counting. It's the counting again. All I have to do, if there's 9 of them, is count out 3 of them.
I'm fascinated with how we go back to counting as an essential manifestation of a mathematical activity and how it is so essential, which perhaps may be the reason, perhaps, why we start teaching multiplication as repeated, because that's what we do, we count. But we forget that it is also about measuring, which you talked about. We forget that it is also about locating, that you talked about. And it is also with play and being able to explain, where you described how students work around, as an object on the floor. So, and using non-standardized units of measurements. So my next question is about teachers, right? The teachers have this responsibility of teaching mathematical concepts. Based on your experience working with pre-service and in-service teachers, what have you noticed with regards to what needs to be done in terms of, okay, anyone who listens to this, it may be a parent as well, these are the things you need to be careful with, and these are the things you need to be striving for?
Well, first of all, the teacher has to have this complex understanding of multiplicative structure, and that's not at all a given. If people have come through the school system themselves that has given them a limited idea of what multiplication is, then that has to be worked on in order to open up this wonderful world of scaling. I mean, I think probably everything can be done in terms of thinking about scaling or stretching things, probably. But then they have to think about, well, what does the learner, well, firstly, what specific aspect of this do I want learners to understand from this lesson that I'm going to teach, or this sequence of lessons? What specific thing do I want them to understand? What language am I going to use so that I help them towards this idea that is a specific idea that I hope they will learn? What is the language that I have to use? What language would I naturally use? Does that go there, or does that do something else? Does that confuse things? This word times. What is times what? What does times mean? This word lots of that we sometimes use. What does lots of tell them? What does it offer, or what does it confuse? So that has to be part of the planning. Then the image. What does this image offer? What does it confuse? I mean, even that image of the bars, if you put a 0 at one end and 1 at the other, there are different questions that can be asked than if you just leave it as the relationship between the lengths. I really have to think that one through. What am I going to say? How am I going to say it? And one of the things that's going on here in the UK is the idea of STEM sentences, that some of those specifics can be turned into sentences so that different situations which are offered, whether they're manipulative materials or whether they are number line diagrams or whether they are symbolic, that the language is always the same, because the language is the thing that I would like them to learn. And it's that language that I would like them to come out with. I'd also like them to be able to say what that language means. So if I use that language with them, I would like them to be able to pick up 2 Buzz Lightyears, or look at a number on a number line, or look at rows of cabbages, and demonstrate that language in those things which are around in the classroom. So I'd like them to have that relationship between perhaps real objects, diagrams, iconic representations, symbolic representations, and the language that we use. And I'd like to make sure that the language that I use doesn't block them from further learning.
And I guess the other side of the equation is, when you teach, don't conflate it with learning, and make, perhaps produce the adequate conditions for learners to make their learning visible by them using or appropriating the mathematical language in a way that will, you said, demonstrate their deep understanding of what they learned.
Yes.
I have 2 more questions, Anne. I know it's late in England now. The one question before the last one is, what curricular changes would you like to see to better introduce the concept of multiplicative structures? How would you like to see these introduced?
I'm not a psychologist, and I know that the psychologists would have an answer. But because I talk to children, I know that most of those ideas that we've talked about are available to children if you use the language, if you have a conversation, if you find out what they notice, if you use a language with them which makes mathematical sense as well as sense to whatever it is they've noticed, that you can build those things up from the very beginning. And I would think that a mathematically aware early years teacher would be able to do that. There aren't many of those around. I did meet a Cambridge Wrangler. At Cambridge, if you do really, really well in your maths degree, you get called a Wrangler. And there was a Cambridge Wrangler in mathematics, a woman she's dead now. She was very old when I met her, who went to Australia and specialized in early years teaching. And I thought her perceptions were just wonderful. She said every mathematical learning experience whether it's a lesson or whether it's out in the playground or whatever it is, has to start with a puzzle. Now, I wonder whether blah, 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 everything has to start with a puzzle. And then the questions come from that. And oh, now we know this, what else could we know? And more comes from that. I've deviated a bit. Can't remember what your question was. It was about curriculum. Yes. So that's one aspect of the curriculum, is to make sure that the experiences that embed multiplicative structure happen long before the formal arithmetic, long before the learning of times tables. Yes. Long before that, so that when you get to the formal arithmetic, people know that what you're doing is something they already understand.
And it really builds on quantitative relationship rather than...
Really, absolutely, it builds on quantitative relationships. So if you know that you're going to have to teach ratio to 10-year-olds, that you start building in the experiences and the conversation when they're 7. In fact, you can do it before by sharing out things unequally and that kind of thing, so that you're bringing forward those material understandings into the formal arithmetic that you're going to be doing. That's what I would like to see a curriculum doing. And added to that, when it does get formal, I'd like to see addition and subtraction taught together, because they are ways of expressing and calculating a relationship. I'd like to see multiplication and division taught together, so that the business of dividing and then, oops, what do we do if it doesn't go into so-and-so exactly, is just not an issue. That's already been dealt with in the gradual building up of the fractions language.
Mm-hmm. Last question, which is a kind of a summary of what we talked about. So we talked about the idea of sequencing, not only of mathematical concepts, but sequencing numbers, for example, going back to teaching complex mathematical ideas to very young kids. We talked about units, and how it is important to use unstandardized units of measurements to deepen the understanding of multiplicative structures. We talked about quantitative relationship and measures of going back to your term, liquid materials. We talked about symbolic representation, and when you showed that the Cuisinart rods, I was thinking how supportive it can be to develop algebraic thinking in very young kids.
Absolutely. Mm-hmm.
Yeah, which is something people still think, even though we have empirical research that shows very young kids can engage with algebraic thinking, there are still curricular expectations to push it to later stages, which is something I'm hoping to see changed. And you talked about the importance of moving the idea or positioning the idea of fractions to early grades, and shuffling around where the kids themselves, the students, the learners themselves do these activities rather than the teacher demonstrating. So would you do you have some sort of summative last words before we end the interview?
To listen to children's curiosity when given materials to match up or compare or whatever. Compare is a big word in multiplicative reasoning, I think. To listen to their curiosity and to sort of bring gently into it the fact that they are talking about something really important that's got language, and they can use their own language and they can demonstrate it with materials. I think that's important. I would be saying the same, about one of the extensions of multiplicative reasoning is rates of change, which of course varying rates of change leads on to the calculus. And the thing that I think is missed in teaching about rates of change is what happens with variable rates of change. Because most things in the real world where we need to think about their rate of change are variable. We talk about acceleration, deceleration, we talk about rates of inflation, we talk about, exponential growth, all those sorts of things. And there again, you've got a situation where the curriculum seems to be locked in to constant rate of change and linear thinking, when people's real experiences of varying rates of change. And then later on, you do the formal teaching of variable rates of change, and it doesn't join up. And it doesn't join up because it hasn't been used and valued and talked about in the maths classroom until suddenly you have to start differentiating things.
Yeah. So just to conclude, I listening to you, I go back to our first interview where we talked about, among others, the question of what is mathematics? What does it mean to do mathematics? And so I think this conversation now really shed some more light onto the question. And I wanted to thank you, Anne, so much for making the time to meet with me and talk about multiplicative structures and the relationship of this, or how it is reflected in curriculum.
Thank you very much. Well, it's very stimulating, as was the last interview. The questions are very stimulating. The thinking that I have to do to approach it is very stimulating. Thank you very much for setting this up, Olga.
Thanks. Take care.